Hello everyone, welcome to another video of Digital Logic. Today in this video we are going to study about how to prepare NOT gate, AND gate and OR gate by using NAND gate only. We know that NAND gate is a universal gate and any kind of Boolean functions can be performed by using NAND gate only. So we are going to prepare NOT gate, AND gate and OR gate by using NAND gate. That means we are using NAND gate to perform Boolean inversion, Boolean multiplication and Boolean addition. So let's start our video. First of all, we will discuss how to prepare NOT gate from the NAND gate. But before preparing NOT gate from the NAND gate, let's see what is the truth table of our NOT gate. This is our truth table for the NOT gate. So we will use NAND gate to produce exactly the same results as the output of our NOT gate. For this we have two methods. Our first method is this one. You can see here both the input of our NAND gate is merged into a single input and both the input is named as A. Because both the input are merged into single one, so the name of both the input of our NAND gate will be the same, that is A here. And the output of our NAND gate will be Y is equal to A dot A complement. Let's verify this by using the value 0 and 1 for our input. So if our input is 0, then both the input of our NAND gate will be 0. So 0 dot 0 will be 0 and its complement will be 1. Likewise, if the input is 1, then both the input of our NAND gate will be 1 and 1 dot 1 will be 1 and its complement will be 0. You can see it here, the output of our NAND gate is exactly same as the output of our NOT gate. You can compare the result to the truth table of NOT gate. That means if both the input of our NAND gate is merged into a single input, then the NAND gate will act as NOT gate. We also have another method to do this. Our next method will be this one. In this method, any one of the input of our NAND gate will always be high. I have kept here B as high, but you can keep A as high also. The output will be the same. So let's verify this by using the value of our input A and B. If the value of input A is 0, the B is 1, because we are not going to change the value of B here. The B will remain high always, and A dot B will be 0 and its complement will be 1. Likewise, if the value of A is 1, 1 dot 1 will be 1 and its complement will be 0. This is exactly the same as the output of our NOT gate. So by this method also we have prepared the NOT gate from the NAND gate. That means we have two methods to prepare NOT gate from the NAND gate. Our first method is that when we merge the two input of our NAND gate into a single one, then also the NAND gate will act as NOT gate. Likewise, if any one of the input of our NAND gate is kept high, then also it will act as NOT gate. Now we will move toward our logic gate simulator, where we can see both this method and compare the result to our original NOT gate. This is my original NOT gate here, and this A is my input and this Y is my output. Likewise, this is my first method to prepare NOT gate from the NAND gate. Here A is my input, in which both the input of my NAND gate is connected. That means both the input of our NAND gate is merged into a single input A, and Y is our output. Likewise, this is my second method of preparing NOT gate from NAND gate. Here you can see B is high. I will keep B always high. I'm not going to change the value of B here. So let's see. If the value of A is 0 in all the cases, you can see in the original NOT gate the output is high. Likewise, in the first method also the output is high. In the second method also you can see the output is high. Now if the value of A is high in all three cases, the output in all three cases are low. That means this first method and second method is equivalent to our NOT gate. Now we will prepare AND gate by using NAND gate. To prepare AND gate from the NAND gate, we will use two NAND gates. But before preparing the AND gate by using NAND gate, let's check the truth table of our AND gate. This is our truth table for the AND gate. Now we will produce exactly the same output by using NAND gate. So we will use two NAND gate here. My first NAND gate will be this one, You can see here A and B represents the input for my NAND gate, and Y is equal to AB complement represents output of my first NAND gate. And the output of my first NAND gate has to be connected to the second NAND gate. This is my second NAND gate. You can see that in the second NAND gate I have merged the input into a single one. The output of my first NAND gate is connected to the input of my second NAND gate, and both the input of my second NAND gate is merged into single. So the second NAND gate is acting as NOT gate, because we know that when both the input of NAND gate is merged into a single one, it will act as NOT gate. So this is a NOT gate and it will invert its input. So our input is AB complement and the output will be AB double complement, because second NAND gate is inverting its input and the input is AB complement. Let's verify this by using the value of A and B. Here you can see we have four combinations for the value of A and B, and they are 0, 0, 0, 1, 1, 0 and 1, 1. We have to calculate our final output, and our final output will be AB double complement. So we will calculate step by step. First of all, we will calculate A dot B. You can see A dot B will be 0, 0, 0 and 1. This is Boolean multiplications of our input, and its complement will be 1, 1, 1 and 0. Again, its complement will be 0, 0, 0 and 1, which is exactly the same output of our AND gate. You can compare it to the truth table of AND gate. So we have prepared our AND gate by using the NAND gate. Now we will move to our logic gate simulator and we will verify the result of these combinations to our original AND gate. This is my logic gate simulator. This above one is my original AND gate, and this below one is my combinations of the two NAND gate, which will act as an AND gate here. This A and B are my inputs, and this is my first NAND gate here, and the output of my first NAND gate is the input for my second NAND gate, and you can see here the input of my second NAND gate is connected to the output of my first NAND gate, and this will be my final output for the combinations of these two NAND gate. Likewise, this is my original AND gate, and this A and B are my input and Y is my output for the original AND gate. So let's verify output for both the cases by changing the value of A and B. Here you can see both the value of A and B are 0 in both cases, and the output is also 0 here. Now I will make the value of A as high, that means 1. A is high here, A as high. In both the cases you can see the output is still 0. Likewise, when both the B is 0, when both the A is 0 and B is high, then also the output is 0 in both the cases. And when both the inputs, that is A and B, are high, then the output in both the cases is also high. That means the combinations of these two NAND gate is acting as our AND gate. To prepare OR gate from the NAND gate, we will combine the three NAND gate here. But before preparing OR gate from NAND gate, let's check the truth table of our OR gate. This is our truth table for the OR gate. And to prepare OR gate from the NAND gate, we will combine three NAND gate. My first NAND gate will be this one. Here you can see both the input of my first NAND gate is merged into a single input. So this NAND gate is acting as NOT gate. That means its output will be A complement. Likewise, my another NAND gate will be this one. In this case also, both the input of my NAND gate is merged into a single input B, and its output will be B complement. These two output, A complement and B complement, of our first and second NAND gate is the input of our third NAND gate. And this is our third NAND gate, and its output will be equal to A complement dot B complement to the whole complement, because we know that the output of NAND gate is the complement of n operations of its input. And here in this case we have two input, that is A complement and B complement, and its AND operation will be A complement dot B complement. So our final output will be Y is equal to A complement dot B complement to the whole complement. Let's verify this by using the value of A and B. Here we have two inputs A and B, so the possible combinations for the inputs are 0, 0, 0, 1, 1, 0 and 1, 1, and its complements are this one. A complement will be 1, 1, 0, 0 and B complement will be 1, 0, 1, 0, and we are calculating A complement dot B complement to the whole complement, that is our final output equal to this one, which is exactly the same output of our OR gate. You can compare the result to the truth table of our OR gate. Now we will move toward logic gate simulator and compare this result to our original OR gate. This above one is my original OR gate, and this A and B are my inputs and Y is my output. Likewise, this is the OR gate prepared by the combinations of three NAND gate. This is my first NAND gate, and this will be my second NAND gate, and this is my third NAND gate. The input of first and second NAND gate is merged into a single input, that is A and B. And the output of first and second NAND gate is connected to the input of my third NAND gate. And this Y represents our final output for the combinations of the three NAND gates. Here you can see both A and B are 0 and the output is 0. When A is high in both the cases, you see the output is high. Similarly, if A is 0 and B is high in both cases, you can see the output is high. And also when both A and B are high, then also the output is high in both the cases. So these combinations of the three NAND gate is producing exactly the same output as produced by our original OR gate. Hence, the combinations of three NAND gate in this way represents the OR gate.